Hello and welcome to our lesson on rational functions with oblique asymptotes. So just as in the last topic we saw some rational functions that looked a little different than we had expected on the graph, that's going to occur in this lesson too. So what I want to do is draw your attention to this first example that I have written here. If you graph that rational function, nothing looks strange about it, right? Graph that rational function, and last time the strange thing was the top was factorable, but here there aren't going to be factors of a positive 3 that make a positive 2, so it's a different strangeness caused by a different effect. But if we look at this graph, so 3x squared plus 2x over plus 1 over x minus 6, so it doesn't look like the linear function with the hole in it, and that's what we saw happen last time. It still looks like a rational function where we see some branches. Now, one piece of this does hopefully make sense. The denominator still can't have an x value of 6, so if x can't be 6, we should still see a vertical asymptote at x equals 6, and we in fact do. But remember what happens when the degree of the numerator, which here is 2, and the degree of the denominator here is 1. When the degree of the numerator is bigger than the degree of the denominator, there is no horizontal asymptote. And hopefully we can see that here. There isn't any place I could put a horizontal line that would match up with those branches. But there is a second asymptote. It's just not horizontal. The second asymptote that happens in this particular graph is what we call an oblique asymptote. The other name for an oblique asymptote is a slant asymptote. It's a linear equation. It's a slanted line. It's not just like a y equals 2, that would be a horizontal line. It's going to be a y equals mx plus b type of thing. In fact, in this case, it ends up being y equals 3x plus 20, and you can see how the branches are approaching that slanted line. Okay, now I'm going to tell you how to find those in just a minute, but these types of asymptotes will occur. They can never occur in conjunction with a horizontal asymptote because they're going to occur, or they can only occur, when the degree of the numerator is exactly 1 more than the degree of the denominator. So since the degree of the numerator is bigger than the degree of the denominator, we won't have a horizontal asymptote. And we need it to be exactly 1 more. Okay? So a slant asymptote or an oblique asymptote. An oblique asymptote, again also called a slant or slanted asymptote, is a slanted line that the graph will approach but not cross, just like the horizontals and the verticals. These can only occur, but I want to highlight they won't always, but they can only occur when the degree of the numerator is exactly 1 more than the degree of the denominator. And because the degree of the numerator is greater than the degree of the denominator, there will not be a horizontal asymptote. So obliques and horizontals can never happen at the same time. Okay? So when we see the degree of the numerator is exactly 1 more than the degree of the denominator, we could be looking for a slanted or an oblique asymptote to happen. But that won't always happen. So it's going to happen in the first one, and I showed you the picture confirmation a second ago. This one is going to have an oblique asymptote, and I'm going to abbreviate this OA. So this is going to have an oblique asymptote, and we'll figure out where it is in a second. This one's going to also have an oblique asymptote, and I could show you with Desmos, but it's going to happen. This third one, however, is not. So we have a degree of 3 versus degree of 2, that's what we need. Degree of 2 versus degree of 1, that's what we need there. Now here we also have degree of 2 versus degree 1, but this last one is different. So I could not factor the numerator here. I could not factor the numerator here. That degree of 3 is only going to work out there if we have difference of cubes or a sum of cubes. The trinomial is going to have other properties in order to be factorable. We're generally looking for a square there or a fourth degree or some even degree to be there. But here, this is factorable. So even though the degree of the numerator is exactly 1 more than the degree of the denominator, because this one factors into x plus 3, and x plus 1, it's not going to have an oblique or slanted asymptote. It's going to be a rational function with a removable discontinuity. So again, these obliques can only occur when the degree of the numerator is exactly one more than the denominator, but that doesn't mean they have to occur. So we want to make sure that the function isn't factorable and reducible before we decide if there's going to be an oblique asymptote. And also, if you just graph it first in Desmos, you're going to see whether or not one of these slanted asymptotes is happening. Okay, so if we have established that we have a slanted asymptote or an oblique asymptote, how do we go about figuring out where that is? Well, we're going to do what the problem is asking us to do. Technically, the fraction bar in our function, that's division. So we're going to divide. We're going to divide our numerator by our denominator to get the linear equation for our oblique asymptote. And when we do this division, we're going to ignore the remainder. Now this might be a bit of a problem for you because I don't know when you've last seen how to long divide polynomials. So that's the way we're going to have to do this, long division. So I'm going to do a little review for you in case it's been a little while. So let's say we had x squared plus 3x minus 5 in our numerator, x plus 1 in our denominator, and I want to divide that numerator by that denominator. So in this case, we would call this the dividend. Okay, the numerator is also called the dividend when I write it like this, and then this is the divisor, and this is what would have been in our denominator. So the thing that does the dividing is our divisor. Okay, so long division, we're going to set this up just like we would set up normal long division. Actually, let me show you normal long division first, okay? If let's say I wanted to divide 1,257 by 4. To set up long division, 4 would go outside of the box, 1,257 goes inside the box, right? So that part's easy. Now when we start this, we start with division. So we divide first. Now I'm not going to look for how many times 4 goes into the whole thing, otherwise I wouldn't need long division. So I'm going to start by just how many times it goes into this first part here, right? So 4 is going to go into 12 3 times. That's going to be the first part of my answer, which we call the quotient. So after I divide 12 by 4 to get 3, what do I do with the 3? Well, I multiply, and 3 times 4 is going to give me a 12 to go here. After I multiply, I need to subtract this 12. So I divide, multiply, subtract. And I got nothing left there. I bring down the 5, and then I repeat those same 3 operations. So I'm going to take 5 divided by 4 to get 1. So I divide it again. Then I'm going to multiply 1 times 4 to make 4. So I multiply it again. And then I'm going to subtract. 5 minus 4 is going to be 1. So I subtract it again. And then I bring down the 7 and go again. 4 into 17 is 4. So I divided. And then 4 times 4 makes 16. So I multiplied. And then I subtract. And then I get 1, and since there's nothing left to bring down, we can call 1 the remainder. Now I know I could make a decimal and keep going, but we won't do that with polynomials. Our remainder, if we don't want to make a decimal, is written as a fraction over our divisor, which in this case is 4. So this would be exactly 314 1/4. Okay? So it's the same 3 operations repeated over and over until we have a remainder, which goes over our divisor. We do the same exact thing with polynomials. Okay? So how does this look with polynomials? It looks a little worse, but it's the same process. So we're going to start by setting this up. Put the divisor outside of the box, and put the dividend, x squared plus 3x minus 5, inside the box. And we start with division. So we divide. Now when we divide, I'm only going to be dividing the first term of the dividend by the first term of the divisor. So it's just an x squared divided by x. Now what is x squared divided by x? Oops. What is x squared divided by x? Well, 2 minus 1 is 1. That's just going to be x to the first, right? So x to the first is going to be the first part of my answer. Okay? After I divide and I get that number that's part of my answer, what do I do with it? Well, I multiply. Okay, now when I divide, I'm only looking at these first terms. But when I multiply, I want to multiply by the entire divisor. So the x times the x, which is going to give me an x squared, and the x times the 1, which is going to give me a 1x. And let me just get this all to be in the same color. So x times x was x squared, x times 1 was 1x, and after I multiplied, I had to subtract. So just be careful because we're subtracting a couple different things here. So I'm going to draw this line and make sure I subtract both of these terms. So x squared minus x squared makes those cancel. And then if I have 3x's but I subtract the 1x, that's going to give me 2x here. and then I'm going to bring down my next term and do it again. So I'm going to divide, and when I divide, it's just the first I wanted a highlighter. Just the first term divided by the first term. So 2x divided by x. What is 2x divided by x? Well, that's just 2. So a plus 2 is going to go here. And then I'm going to multiply that. So 2 times x and 2 times 1. Okay, 2 times x is going to be 2x, and 2 times 1 is going to be positive 2. And then I got to subtract again. So I'm going to draw my line here, make sure I subtract both of these terms. These will cancel, and the negative 5 minus the 2 is going to give me a negative 7. And since there's nothing left to bring down, the negative 7 is my remainder. Now, what we're doing with this division is looking for an oblique asymptote. We're looking for a linear equation as our oblique asymptote, and that is going to be the quotient. The quotient is our equation for our linear or slanted or oblique asymptote. The remainder piece is minus 7 over x plus 1 here is not going to affect our oblique asymptote. Okay, so let me try to help you understand what's happening here. We just took x squared minus 3x plus 3x minus 5. Cancel. Come on. Plus 3x minus 5, and I said let's divide it by the x plus 1 here, and we got x plus 2 and then a remainder of 7. So this ended up being x plus 2 plus a remainder of 7 over our divisor, which was x plus 1. Okay? So what I'm telling you here is these two are the same function in different forms. So this rational function, if you were to put it in Desmos, this rational function, if you were to put it in Desmos, the same function, they're just written in different forms. Just like I could say 48 divided by 6 is exactly 8, these two have the same exact value. Okay, they just look a little different. So why does x plus 2 end up being a slanted asymptote for us? Well, let's go back to our parent function. Okay, our parent rational function was just 1 over x, right? If I say put a plus 1 here, what happens to our function? Well, it shifts over to the left 1. And if I multiplied by 7, which that 7 would go to the top of the fraction, right, 7 over x plus 1, then not only am I shifted to the left 1, but I'm also going to be vertically stretched. Okay, so this piece here is so far just two transformations of our parent function. All right, now if I wanted to make this graph go up, let's say 2, then I'd put a plus 2 here. Or if I wanted my graph to go let's say down 4, then I would put a minus 4 here, and then my horizontal asymptote would shift down to negative 4. Well, now instead of having some constant being added or subtracted to our transformation of our parent function, we have this whole line that we're putting here. So instead of having some horizontal asymptote that has shifted from 0 up to 2 or down to 4, we have a new slanted asymptote instead of that horizontal. So this is a transformation of the parent function, and this represents, instead of our horizontal asymptote, our oblique asymptote. Okay, so I don't know if that makes sense, but that's where this is coming from. So we don't really need this remainder. It's not really affecting the asymptotes of our graph. And we can see the vertical asymptote here and vertical asymptote here, they haven't changed. It's just we're using this to identify the slanted asymptote. Okay, so to finish up the division, we bring down the next term, and we keep doing our divide, multiply, and subtract until we have a remainder, but as mentioned here, the remainder gets ignored in terms of finding the oblique asymptote. So let's try that process out here. I actually don't have to go through all of the division. As long as I can get this linear equation, I'm going to be done, because that's going to show me where our asymptote is. So let me set this up. Let's see, 3x plus 2. Again, I know this is going to have an oblique asymptote. The degree here is 2, the degree here is 1, and there won't be any factors of positive 30 that are going to make negative 1. So to get positive 30, they'd have to both be positive or both be negative, and they won't make negative 1, so not factorable. Okay, so this is going to have an oblique, and let's figure out where it is. Let's take our numerator and divide it by our denominator. So first, it's going to be 6x squared divided by 3x. And 6x squared divided by 3x is going to give me a 2x here. And then I'm going to multiply 2x times 3x and 2x times 2. So 2x times 3x is 6x squared, and 2x times 2 is going to be 4x. Now I have to subtract. So I'm going to subtract this, subtract that. Those cancel. And then negative 1 minus 4 is going to give me negative 5x's. And I'm going to bring this down, and then I'm going to end this process with the next step. So the next step is the division again. And if I divide my first term by my first term, negative 5x divided by 3x is going to be negative 5/3. So I'll do that. So that's going to be a negative 5/3. And I could multiply and keep going and get the remainder, but I don't need to. All I needed was the equation of the line where my oblique asymptote is going to be, and that's that quotient. So this graph is going to have an oblique asymptote at this linear function, y equals 2x minus 5/3. Okay, now let's just confirm and make sure that that looks right. So let's put in our y equals, make a fraction, 6x squared minus x plus 5 over 3x plus 2. So I can see there's definitely going to be a slanted asymptote in there. Let's just make sure we calculated it correctly. So y equals 2x minus 5/3, and that looks right to me. You see how those branches are approaching the asymptote there? All looks good, okay? Alright, let's try that again. So degree is 2, degree is 1, top's not going to factor, so this is going to have an oblique asymptote, and let's divide to figure out where it is. So x minus 4 into negative 3x squared plus 4x minus 5. So negative, sorry, highlighter please, negative 3x squared divided by x is going to be negative 3x. Negative 3x times x is going to be negative 3x squared. Negative 3x times negative 4 is going to be a positive 12x. I've got to subtract those. So if I subtract here and subtract here, minus a negative is going to make that a plus. So those will cancel. And 4 minus 12 is going to be negative 8x here. Technically this is coming down, but I only have to go one more step. What's negative 8x divided by x? That's going to be a negative 8. So there it is, the equation of a line. So this is going to have an oblique asymptote at y equals negative 3x minus 8. And again, if we wanted to put that into Desmos and confirm it, we could do that. Alright, so this would be a good opportunity for you to pause the video and try the next one. See if you can handle at least part of that division to figure out where the oblique asymptote is on this function. So x plus 2 into x squared plus 7x minus 3. X squared divided by x is going to give me an x. X times x is x squared. X times 2 is going to be 2x. Now I want to subtract this. So subtract, subtract, those cancel. And 7 minus 2 is going to give me 5x. And now I just have to divide the 5x by x. 5x divided by x is going to give me a positive 5. And that's it. Don't have to go any further because I have the equation for my line. So oblique asymptote at y equals x plus 5. And again, all could be confirmed with Desmos. Okay? So if we can find the oblique asymptote, we already know how to find the vertical asymptote, then we should be able to use that information along with Desmos to create a graph. So let's try that next. Okay? To graph, we want to make sure first that the function doesn't simplify. Let's make sure it doesn't have a removable discontinuity before we go about assuming it has an oblique asymptote. And if you really weren't sure how to do that, just put it in Desmos first. Then we're going to find and graph the vertical asymptote because that's relatively simple for us. Then we're going to find and graph the oblique asymptote, and using the slope, which is m, and the y-intercept, which is b. And then we will use Desmos to confirm, and then also what you're putting in Desmos is what you're going to screenshot and submit in your practice assignments. Okay? So this graph, let's see, there aren't going to be any factors in -8 that make -6. No, so not factorable. So this is going to have a vertical asymptote. Let's find that one first. Let's see, a vertical asymptote is a value of x that makes our denominator, in this case 4x plus 5 equals 0. So 4x equals a -5, x equals -5/4 is where our vertical asymptote is going to be. And then the oblique we're going to find with division. So we're going to take 4x plus 5, and we're going to divide it into -8x squared minus 6x plus 1. So first, -8x squared divided by 4x is going to be a -2x. -2x times 4x is -8x squared. -2x times 5 is going to be -10x. And then I have to subtract. So I'm going to subtract. That's going to make positives. Two double negatives there make positives, so these will cancel. And then -6 and +10 there is going to make 4x. And I could bring that down, but it doesn't really matter. 4x divided by 4x now is going to give me a +1 here, and there it is. So I'm going to have an oblique asymptote at y equals -2x plus 1. Okay? So vertical asymptote at x equals -5/4. If you don't like the fraction there, that's -1 1/4 or -1.25. So -1.25 is going to be like here-ish. There's my vertical. And then the oblique asymptote is going to be at y equals -2x plus 1. So y equals -2x plus 1 has a y-intercept at 1. So I'm going to make a point there at 1. And then if my slope is -2 or -2/1, that means I can go down 2 and right 1 to make my next point. So down 2, right 1, and I can make my next point. And I can do that as many times as I need, and I can work backwards here so that I can try to graph my oblique or slanted asymptote. Okay, so there's those guys. And now I just need to put the branches in. I'm not exactly sure where they're going to go, and I could test some points, but this is going to go into Desmos anyway. So let's put it in Desmos. Alright, so we have y equal to a -8x squared minus 6x plus 1, and then 4x plus 5 in the bottom. So there's my branches. Now let me just put the asymptotes in just so we can see it all really well. We said x was going to equal a -5/4. That looks correct. And we said for the oblique y was going to equal -2x plus 1. Alright, so all that looks good. Let me just zoom a little bit here so you can get a good picture. All that looks good. Okay, now let me just fix the colors and fix the dotted lines. So I'm going to make this black. I'm going to change this to, what did I have on my paper? I had that red. And let's make it a dotted line because it's an asymptote, not really part of the graph. And this is the one on my paper I had in blue. And again, let's make that a dotted line. So I can see that my branches have to go into little skinny sections there, right into the little skinny sections between those asymptotes, but everything else on my paper looks correct. So I'm just going to put my branches in, and then I'm good to go. So I'm going to squeeze a branch in there, and again squeeze another branch in there. And there it is, okay? So there's what would be on paper, but in Desmos, again, and what you're going to submit for your practice assignment, and make sure you're showing me the branches, make sure you're showing me the vertical and the oblique asymptotes, make sure they're graphed with dashed or dotted lines, and all the equation stuff underneath the graph. I want to see all of that in your screenshot, okay? Alright, I got one more here, and again, if you feel good about this, then give it a try. So a vertical asymptote, where is that going to happen? Well, what's going to make x plus 1 equal 0 would be a -1. So a -1 on the x, we're going to have a vertical asymptote there.
The oblique asymptote we're going to find with division. And again, I know this thing is not going to simplify because there aren't any factors of 2 that make 4. So I'm going to take x plus 1 and divide it into x squared plus 4x plus 2. So x squared divided by x is going to be x. X times x is x squared. X times 1 is 1x. When I subtract that, these will cancel. And 4 minus 1 is going to give me 3x. And 3x divided by x is going to give me a positive 3. So this oblique asymptote is going to be at y equals x plus 3. Okay? So slope, or y-intercept of 3, and a slope of 1 means I can rise 1, run 1, make the next point. So I can make as many as I need here to create that oblique or slanted asymptote. And now let's go to Desmos to confirm everything. So y equals x squared plus 4x plus 2 over x plus 1. And now I have these really wide branches this time. So confirm x equals -1 is our vertical. That looks good. And then confirm y equals x plus 3 is our slant. And that all looks great. Now let me just get it to look more like my paper here. So I'm going to make these branches black, and that's just by choice, doesn't matter. You can really make these whatever colors you want. But I'm going to make this one red because it's red on my paper, and make sure it's dotted. And I'm going to make this one blue because it's blue on my paper, and again, make sure it's dotted. So that's the picture that I almost have on my paper. That's what I want to see in your screenshot for Desmos. Okay, I just need to sketch my branches in, which are in the wider sections this time. So this time, I'm going to have a branch in here, and a branch out here. Something like that. Okay, just a sketch of those branches is going to be fine. And there it is. So make sure you're showing me all that stuff in Desmos because I can't verify everything that you're doing on your paper. Alright, if you want full points anyways, that's what you're going to show me. Okay, so you've got some problems to work on in your practice assignment. Give them a shot, and if you need some help, just reach out.